Right, so my talk summarizes a work of about a year developing a new workflow to tackle earthquake simulations. Obviously, a year is a long time, so I won't be able to get into everything in any particular detail, but I want to summarize the key takeaways that we learned through this year of developing a workflow that hopefully you guys can take into your own computational workflows. But first I want to bring into some context. So I work with a team of about 5 software engineers, and we work together with researchers at the University of Canterbury's Civil and Natural Resources Engineering Department with a primary focus on ground motion simulations. That's simulations of earthquakes. And we developed 2 key research products. The first is CyberShake New Zealand. CyberShake New Zealand is a large-scale simulation of earthquakes across the country to get a better idea of earthquake hazard. And the scale is huge. So we're talking in the old model from 2010, something like tens of thousands of earthquakes simulated, possibly dozens of times. And in the new model, we have hundreds of thousands of earthquakes sourced from EQC. And we're still figuring out how we might simulate all of those. But we also have researcher outputs. So like I said, we work with a team of researchers who are often PhD and postdoc students, and they have their own independent research goals. There's a huge array of things they do, and they take parts of our CyberShake workflow, the code we developed to do CyberShake, and they mix and match it to suit their own needs. So we simultaneously have to work with both a very large-scale computational workflow that's fixed and a lot of small-scale workflows that change. And the big picture here is that for CyberShake New Zealand, we're looking to provide better estimates of seismic hazard in different parts of the country, which should hopefully inform things like EQC and disaster response. I realize EQC is dead now, so it's a different thing. And the researcher outputs are for advancing geoscience and ultimately, hopefully, improving CyberShake as well. To do that, we had an old simulation workflow that grew very organically for our needs over time. And it's reasonably complicated. If you can't read the diagram, it doesn't matter. But it involves a number of components that were each bespoke for every single researcher and then separately also for CyberShake. So when you see this, imagine like half a dozen of these workflows, each of them slightly different for each person. And they all interact with a lot of state. So we have state from the HPC. We don't really get to control that too much, but that's the underlying software that runs our code. We have our own custom code to do simulations that sits on top of the HPC environment. We have job management. We had a custom solution for that. You notice I'm saying the word custom a lot. And simulation configuration that was also very custom and very complicated. And that created a lot of problems for us. And the problems were, first of all, it was designed for CyberShake and then eventually adapted for researcher needs. Problem with this was that it made it very difficult to get researchers to work with it on their own. There was a lot they needed to understand to do their own research, to run their own simulations and develop their own results, and that often meant that members of the software team were looking after their work for them. There were entirely custom solutions for pre-solved problems, and some of that was because we were relying on versions of, for example, Python that were very old, and so libraries that were available to other people weren't available to us, but part of that was also a bit of a not invented here syndrome. Complex, brittle, and hard to reproduce. I'll get onto this in a second, but yeah, there's a lot of moving pieces and lots of them could break. They often did break, and so a lot of our time was spent fixing them to work. And a lot of legacy code, just a lot of legacy code. Code from a number of years ago, code that was developed with one purpose and then stretched long beyond what its useful lifespan was. And so just to illustrate the problem, we had a challenge to reproduce a 3-year-old simulation, and it required our team lead, Sung, who's over there, basically his whole year. It was just doing that. And we needed to develop special tools to rederive input values for files and the configuration that went missing in the intervening time. And it was ultimately totally impossible to do this perfectly due to changing software on NeSI's side in those 3 years. So, you can't really reproduce it exactly. And this is a picture of him presumably taken before he had to do all this reproduction work. And so last year we took it upon ourselves to essentially start from scratch, throw away, not all, but most of the old code and redesign a workflow with all of the lessons we'd learned in the intervening 4 years and using some a model based in Southern California. It's called SCE, Southern California Earthquake Center, and build a new thing. And the key part of this new workflow, and the thing that I think guided us a lot to the eventual development is the idea that you can separate a simulation, or in general most scientific workflows, into three core components that you ideally want to be independent and reproducible. The first is the software side. You need a reproducible software environment that you can cargo cult around with you and not have to reproduce painstakingly on every HPC you start working with. You need a reproducible software execution control flow, and that's actually really hard. This is the job management side of things. We tried to do that ourselves, and that was a huge mistake, so ideally we'd like to find something that wasn't developed by us, managed by other people that did this for us. And then inputs. So the inputs to your simulations need to be completely defined. They should be easy to read and understand. It should be clear when you look at a simulation, all the different inputs that went into it, including things that were undocumented that, command line arguments with default parameter values, that kind of thing. So for the software side, we decided to look at containerization, and I understand the next talk is also on containers, so I'm going to not spend too much time belaboring this point, but basically we focused on shifting all of the software into Aptana containers for our workflow, and this had a huge improvement because Aptana containers are just a single file. So you can copy them over to a new research compute center and then spin up an exact copy of the same simulations you were doing on, say, NeSI or on your own local computer. It dramatically simplified the process of environment management, which took up a majority of what we were doing managing the researchers day to day. And of course, because it's a single file, we can archive it along with Cybershake releases so that we can go back and reproduce old Cybershake releases as they were 3 or 4 years ago. Silk. So Silk was what we decided to replace our job management software was, and it's a massive improvement to our research user experience. So this was developed at NEWA. It's maintained by, I think, about 6 or 7 people. And it's really well fleshed out for the process of starting simulations, restarting simulations. In particular, that part where you run a simulation and something breaks, and then you have to go fix it and then restart that. In the old way we used to do things, it usually involved one of the software team members to jump in and fix it for them. But at least anecdotally, I've been able to get researchers to do this themselves now, which is a huge improvement for our time can be spent developing a workflow rather than managing ones that are already running. And it's also composable, and I'll get back to that in a second, but you can build up workflows out of smaller workflows using templates. And we used to have our input specifications for simulations used to be spread over a large number of files, and some of those files overrode each other. And so when researchers would come to us and say, what was the input you used for running the high-frequency portion of the earthquake simulation? We could say, well, it's probably in this file, but if that's missing, it might be in this one. And you've got to check further up the chain of input files to make sure that none of them have been overwritten at some point. And so in the new format, we decided to throw that out and focus on just one file. Every simulation has one file that completely specifies all of the input parameters. And this massively improves both the reproducibility of simulations, because you only need to archive one file and you can't forget to archive one of the smaller files. And also it makes it much clearer what the inputs are, because nothing's being overridden, there's no state in the process. And so workflow planning. So one of the key problems, the key challenge with our workflow is that we have to build something that works for Cybershake, which is very fixed, and for researchers. And every researcher has their own special little snowflake workflows that come out of what we make for Cybershake. With the old workflow, everything was monolithic, so we couldn't break it up and reuse parts of it for other workflows. Because Silk has a composable templating design, we can actually build little CLI tools that compose workflows out of workflow stages we've written. So the workflow planner that I spent a lot of time writing can take the big Cybershake workflow graph and then pull out different parts of it and stitch it together in a way that makes sense. And then it has visualization tools that allow researchers to look at that workflow that's been put out and check, is it doing all the stages I expect it to do? Are the stages that I'm hoping to archive on Dropbox eventually going to be archived on Dropbox? And so this means that the entire workflow from end to end, from I want to run a simulation to the results are done, can be run in a way that doesn't require input from the software team. And so we're able to focus on doing what we're supposed to be doing, which is developing new scientific code to run more simulations. The other thing we looked at a lot was testing, and I don't have too much time to go into this, but hypothesis testing was a huge improvement to the testing of the code that we write. It's essentially very fancy brute force for your unit tests, and the hopeful outcome of this is that it would save us hundreds of thousands of wasted core hours on buggy code that eventually we have to rerun. Just as a very small example, if you have a little formula here, this formula, you throw in a number, it gives out a prime number. Problem is, it doesn't work. You can try it for a lot of different numbers. The traditional approach to this would be a unit testing approach. You might write a couple of unit tests where you check it for a few numbers, but you might miss it. And hypothesis testing lets you check all the possibilities all at once, and then not only will it find where your code is broken, it'll find the smallest case where your code is broken, which, at least from our side of things, when we go to find the cause of a bug, helps enormously because it gives us something very tiny and reproducible, something we can fit in our head and then think about a little easier than just, if you put 1,000 in, it doesn't work. So what are our key takeaways from developing this new workflow? The first is you should make your workflows declarative. There shouldn't be any state in the workflow management. There used to be state in our workflow management with this SQLite database we used to manage jobs, and it was a nightmare. It would fall apart if you broke something in the workflow, and then it would require one of the software team to come and fix it. So it should be declarative. Your workflow should be composable. So making smaller parts of the workflow and then stitching them together is actually much better from an engineering perspective than trying to do the whole thing end to end. This might sound kind of obvious, but it's very easy to do when you develop these things organically without too much thought. And so I think just putting a little bit of thought in and composing out of smaller pieces helps improve your design. Automate your testing. So I don't just mean have testing. Having testing is the standard for good scientific software. Having testing that tests all the inputs, even the inputs you don't like, is helpful. And hypothesis testing, I think, is a really huge improvement in that respect. And design for the least savvy user. So kind of as a quirk of how we designed this workflow, because we were trying to run it on Cybershake immediately because we were worried it wouldn't work, we ended up designing it for the researchers first. And that turned out to be a much better approach because they have fewer, they don't understand necessarily all the software that goes into the project. And so you have to make it easy for them to use. And when you make it easy for them to use, it's actually a more foolproof system that you can build more complicated things out of much easier than trying to tackle the complicated thing first and then making it simpler for the researchers. That was the approach we applied for the old workflow, and the new workflow doesn't have this problem. Yeah, so that's kind of where we are with the new workflow. We're still getting around to running it on new Cybershake, but at least for the moment, it seems to be doing better than the old workflow. Okay.
Thank you, Jake. Did anyone have some questions? Alex?
Thanks, Jake. Couple of questions. I mean, one of them was plan workflows. Is that a tool that comes with Silk, or is that something that you developed on your side? And
Yes and no. So Silk provides Ginger templates for building workflows out of a TOML-like syntax.
Yeah.
And that's great if you want to run many instances of the same workflow. Right. The challenge is if you want to run slightly different workflows made out of little tiny components. So the workflow planner is custom. We wrote that on top of Silk. Yeah.
Yeah. Oh, that's good. And the second one was the hypothesis testing, which seems to give you a full coverage. Is that something that is very expensive to run?
So, I mean, it depends on how you design it. The idea is that for hypothesis testing, you want to be testing properties of your code rather than testing
Values.
Yeah, so things like if you're sorting an array, you want to check afterwards that it's in sorted order. That would be a property of the output of a sorting function. And so that tends to be quite cheap. And much like with unit tests, you want your unit tests to be fast. So yes, it's testing lots of inputs, but if your unit tests are structured correctly, it should be fine anyway.
And is that sort of custom?
No, so there's a Python package called Hypothesis that does hypothesis testing. There's ones for all sorts of languages. If you're interested in seeing where that how you can use that for our software, we use it a lot in the source modeling side. So that's modeling the fault geometry and extracting things like points on the faults and computing distances between faults. And we apply hypothesis testing a lot there. So you can see examples of how that works.
Thank you.